Hi everyone, and welcome to part 2 for our year in review for paleontology. I do want to really quickly mention that we do have timestamps down below in the description, and all of the image credits are given at the end of the video. As for what we talked about last time when we left off, we were talking about the sauropods. So now we're going to talk about something that isn't a sauropod, but was found next to one of the largest sauropods, Supersaurus. Supersaurus has already been described, but very near a specimen of Supersaurus was something that's actually quite diminutive, and that would be one of the earliest Paraves coming from North America. The new species, named Hesperornithoides, has been shown to be one of the earliest of the Paraves, and could actually show us a lot about how the group evolved. The Paraves includes both the birds, but also some very closely related groups, such as the raptors and even the troodontids, which Hesperornithoides seems to belong to. Coming from the late Jurassic Moros information, Hesperornithoides helps to show just how diverse the clade was, and reinforces the idea that the Paraves evolved flight at multiple times, as Hesperornithoides wouldn't be able to fly, but did have long and developed flight-type feathers, meaning that their first evolution probably wasn't for flight. While some other late Jurassic Paraves seem to have been able to fly at least okay, such as Archaeopteryx, what Hesperornithoides might indicate is that flight evolved fairly late along the line, as even things like it that were fairly derived from the initial base that would have been the common ancestor of all Paraves still didn't have flight, meaning that flight would have been a very specialized trait that may have evolved actually a few times in the clade. As for the origin of flight, a new study looked at what would be the most similar animal to many of the early Paraves, and that would be a baby ostrich. By strapping fake wings to the back of a baby ostrich and watching it run, they were able to see what kind of lift would be provided by wings even if flight wasn't achieved, which, to be fair, the baby ostriches still did not fly. What the researchers found is that there was a natural undulating pattern in the lift the wing provided. It naturally caused a rising and dropping motion, which then could have been adapted into the flapping motion for flight. Specifically, the ostrich babies and the wings were designed after the animal Fukuipteryx, which definitely didn't fly, but helps to show how even non-flying dinosaurs that had the beginnings of wings could have still used those wings to help provide lift, potentially helping them run faster or get up steeper surfaces. Another paper highlights this diversity, but specifically in the Dromeosaurs, things like Velociraptor, Deinonychus, and Austroraptor. While similar species, such as Deinonychus and Velociraptor, have been more studied, these represent northern hemisphere species, and so that's why Austroraptor is one of the more important ones in this study. What the study shows is that the southern hemisphere Dromeosaurs likely didn't have the same kind of muscle power driving the iconic claw that would have been on the foot of all Dromeosaurs. Meanwhile, the northern hemisphere Dromeosaurs would have had that power and hunted larger animals, such as Deinonychus hunting Tyrannosaurus. And this isn't just down to the animals being smaller. Austroraptor could grow about as large as Utahraptor, so this is a very specific niche that they filled in the southern hemisphere that wasn't being filled in the northern hemisphere by those Dromeosaurs. There were also a few different birds named this year, including Fukuipteryx, coming from Fukui, Japan. What Fukuipteryx helps to show is a transitional species, somewhere between Archaeopteryx and the more derived birds, such as Confucius ornis from China. There's a number of things that help to show this. As an example, the pygostyle on the tail. In modern birds and in Confucius ornis, the pygostyle helps to create a fan of feathers on the tail, and creates a much more uniform pattern of the tail feathers. Meanwhile, in Archaeopteryx, which lacks any kind of a pygostyle, there would be a divot at the very end of the tail, where the feathers wouldn't be able to grow because there weren't the proper muscle attachments and bone attachments for the feathers to develop there. Fukuipteryx, rather than having the much more rounded pygostyle of something like Confucius ornis, or the more modern birds, had a rod-shaped pygostyle. What this shows is that there is quite a bit of diversity in the early birds, and even something as basic as the basic fan shape of modern birds' tails had to go through several iterations before it finally landed on something that was as efficient as the modern birds have. With so much diversity in the early birds, it also shows just how unique it is that the modern birds that we have today were able to succeed as well as they did, and even survive the KPG extinction. Another bird, not closely related to our modern birds, but rather an Eanthornis which is a separate clade that was more dominant during the Cretaceous, was shown to be quite unique. Although it's a very partial bird preserved in Burmese amber, the fine preservation of amber helps us to show just how unique this bird was. Electornis has been shown to have the longest toes relative to the body size of any bird known. And this is absolutely ridiculous how long the toes are, frankly. They're so long that it's been suggested that their behavior was probably something like that of the modern-day aye-aye, a mammal. The aye-aye uses its long bony finger to reach underneath the bark into tunnels formed by grubs and other bugs beneath wood. It then uses that finger to pull out the bug and eats it. It's been suggested that Electornis did something similar, as there wouldn't be any mammals to already fill that niche, and having a good source of food, even something from grubs, is something that's very valuable for an evolving species that needs to develop its own niche in order to succeed. The month of December saw a paper on the very first forests known, coming from the Devonian period of New York. What the forests show is a series of root systems of different trees, including Archaeopteryx, which isn't to be confused with Archaeopteryx. They are spelled very similarly, but one is a tree and one is an early bird or dinosaur that is almost a bird. The roots of Archaeopteryx show that even these early forests during the Devonian had very advanced root systems, at least in some of their plants. These root systems may have been one of the main reasons for these types of trees to become so dominant, especially during the next period, the Carboniferous, which saw massive forests that increased the oxygen levels in the atmosphere to almost 35%. Meanwhile, some of the other Devonian trees show a much more primitive root system. While these other roots haven't been specifically described, it is very easy to see just how much more basic they are, without nearly as many of the branching roots that you would expect in even modern-day trees. Overall, the complicated root systems of things like Archaeopteryx can help us understand how root systems evolved and just how important it is for us to understand the modern-day root systems that make up our modern-day forests, particularly in the face of climate change, which is affecting many of the modern-day forests. Even older than these trees, though, is the origin of a lot of complex life during the Cambrian. New species were described from the Cambrian, including Cambroraster, which comes from the Burgess Shale, where many very good fossils have been described before. Cambroraster seems to be fairly closely related to Anomalocaris, which was likely the dominant predator of the Cambrian. Cambroraster likely used a much more conservative method of hunting, rather than being as aggressive as it's believed Anomalocaris was. Rather, the sift-like arms at the front of Cambroraster were likely used to sift through sediments and uncover buried animals beneath those sediments and then feed upon them that way. Cambroraster is also unique in having a large shield-shaped projection at the front of the body. While this kind of adaptation isn't unique to Cambroraster, it does help to show just how diverse the early ecosystems would have been, with even something that would have been a predator like Cambroraster being sure to have a defensive adaptation as well in that shield. As for the Burgess Shale, there's also a new series of beds coming from China that have very similar preservation types, but are slightly older. The new fossil beds coming from Xinjiang, China, help to show just how diverse many of the early life forms were, and have some very fine preservation for very unique species, such as some of the first Chino ringworms, which today are very, very small, potentially just a few millimeters long, but during their first initial evolutionary radiation, were as much as 4 centimeters long, which, while it doesn't seem particularly massive, is a very significant change considering how small they are today. There are quite a few species coming from this new site, and so we should be able to look forward to it in the future, providing even more information for researchers. As for the diversity that occurred during the Cambrian, it seems there have been a few different reasons that this occurred. One of the most recently suggested reasons has been tectonic shifts and tectonic plates, creating a large series of volcanic island arcs. These island arcs would have released a lot of different chemicals and nutrients into the water, including phosphorus, which is needed for life. This surge of nutrients would have helped a large number of the photosynthesizing plants develop into many more complex forms, which in turn would have helped lead to the more complex life that evolved during the Cambrian. A lot of this new animal life, though, would have required oxygen, and while the photosynthesizing plants would have helped, it still wouldn't have been totally widespread enough to be consistent, and a new series of beds from the Cambrian do show this. Rather than being a consistent oxygen level throughout the Cambrian, what they show is periodic occurrences of oxygen, that do seem to follow fossil evidence. Oxygen-rich waters would periodically come into the region, and with it, life would follow. However, over time, those oxygen-rich waters would move to different areas, and with that, the life would leave as well. This would occur in cycles, and while the timing on those cycles wasn't exactly consistent, it was at least enough for life to take root. When considering a lack of oxygen in the oceans, though, there's an even greater time period that had a much more significant impact on life, in my opinion at least, and that was the Permian-Triassic extinction. The Permian-Triassic extinction is largely considered the worst extinction of all time. Potentially as much as 95% of life in the oceans died out during it. And now some researchers are suggesting that it started earlier, or that there was another mass extinction just before the end Permian extinction. What the researchers suggest is that what happened in the middle Permian should also count as a mass extinction. Some of the evidence that the researchers used to suggest this are certain types of rugose corals that were tropical dying out during the middle Permian, as well as a few types of sponges that would have used calcite as part of their skeletons. Similar patterns are found on land, with animals like Edaphosaurus and Dimetrodon dying out on land, and being replaced with animals like the Gorgonopsids as carnivore, and things like the Pterosaurs as herbivores. It does suggest that there needs to be more study done on the middle Permian, as it does lead into the Permian-Triassic extinction, which has a lot of similarities to our own modern-day extinctions that are occurring in the face of climate change and pollution, including pollution of things like mercury, which a new study suggests had a major impact on the oceans of the end Permian. One study looked at the amount of mercury in marine sediments coming from the end Permian, and suggests that the end Permian extinction would have taken place on a longer interval than previously believed, rather than being quite as rapid as it may have been suggested in other studies. Specifically, the mercury has been leaked to the eruptions of the Siberian traps, much like the Deccan traps I mentioned earlier from the end Cretaceous, except these were even bigger and probably caused the majority of the extinctions that happened at the end Permian. What it suggests is potentially that the Siberian traps were erupting for a longer period than previously thought, or that potentially the Ameshian traps were also part of the cause of this rise in mercury, and could have very well led to a longer extinction interval than previously thought. Another paper finds correlation between a rise in mercury levels in both terrestrial and marine sediments, and a rise in pollens coming from ferns. Ferns are very commonly associated with mass extinctions, as they're one of the first plants to be able to start to regrow after a mass extinction event and become dominant for a few thousand years at least after the event. The end Permian extinction created a large gap in the number of niches that could be filled by the different animals that did survive, and this led to rapid radiation and evolution in many of the different clades that existed, including one group that seemed to have emulated the modern-day platypus, only 250 million years earlier. Eretmoripus is a reptile that seems to have adapted a very platypus-like lifestyle. It also had small eyes and potentially didn't even use them for hunting, as this paper does suggest. It also had a large flat bill, much like a modern-day platypus. Chances are it did live a similar lifestyle, hunting small invertebrates that would have been living underneath the sediments at the bottom of ponds, streams, or potentially even the ocean, just in very shallow waters. What Eretmorhippus shows is one of the most unique circumstances of convergent evolution, where two species evolved the same adaptations to fill similar niches despite not being related to one another. As for a trait that all animals have is they poop. And this is going to be important in the next two papers, as we're going to be looking at coprolites, which is fossilized poop. The first paper suggests that the non-dinosaur archosaur Smok might have eaten very much like a tyrannosaur, crushing many parts of the bone just like Tyrannosaurus rex did. This has been indicated by the fossilized pieces of bone inside what is assumed to be poop from Smok. While it's hard to confirm that the coprolite is from the genus Smok, it's assumed that it is, as it was the largest predator in that environment at the time that the fossils were found, coming from Poland. These coprolites contain both bone fragments from what is assumed to be the prey animal and fragments of teeth. These teeth are from Smok, and it's assumed that they would have broken off while the animal was eating the bone. There's also some regurgitates, meaning they would have thrown it back up, that have also been fossilized and show similar things, with pieces of bone but also pieces of broken Smok teeth inside of it. This kind of very unique adaptation to be eating bones has only evolved a few times in the fossil record, and only a few times in the Archosaurs. The paper also suggests that behavior like that of owls, which vomit back up pellets, may have evolved very early in the Archosaur line, even as far back as the common ancestor between the dinosaurs and Smok, as it very much seems like Smok may have been regurgitating the more angular pieces of bone that could have been more damaging to the internal systems of the animal. Another paper on coprolites looks at coprolites from a pterosaur, and most likely an animal very similar to Pterodastro, which seemingly would have used its very fine sieve of teeth to filter out small animals from the ocean or from ponds, and would eat those very small invertebrates, much like a modern-day flamingo. When animals like Pterodastro were first found, it was assumed their very unique teeth were used for something like this, and having both pterosaur footprints and the coprolites in close proximity, and those coprolites containing very small fossils and pieces of small invertebrates, helps indicate that this was probably the case. Some of the fossils caught in the coprolite were as small as 0.3 millimeters across, meaning this sieve that was formed by these pterosaurs' teeth would have been very efficient, and helped them to become as successful as they were. And although the pterosaurs did die out of the end Cretaceous, seeing this kind of convergent evolution for very specific niches, such as those filled by modern-day flamingos and these ancient pterosaurs, is something that just shows us how unique different evolutionary paths may take. Things like coprolites are called trace fossils because they just leave a trace of the animal that was there. But they aren't the only kinds of trace fossils. The most famous kind are footprints. One of the most known types of footprints are those of dinosaurs, such as the footprints found in Connecticut at Dinosaur State Park. These have often been attributed to animals such as Dilophosaurus, which was one of the most dominant predators of the early Jurassic. However, a new study suggests that they aren't actually Dilophosaurus fossils, despite Dilophosaurus being the state dinosaur of Connecticut. Rather, what they suggest is that the footprints actually belong to the animal known as Anchisaurus, which was a prosauropod and is actually found in very similar sediments to those that these footprints are found in. Meanwhile, a Dilophosaurus has never been found in Connecticut, meaning either there are a bunch of Dilophosaurus running around leaving footprints everywhere, or it's an Anchisaurus footprint. I just find it slightly humorous that Dilophosaurus is even that state's dinosaur, but they don't actually have any fossils of it. Only Arizona does, and being from Arizona, I am slightly proud of that fact, and partially why I brought up this specific paper. As for other dinosaur footprints, there's another set coming from South America that is absolutely bizarre, and these were described a few years ago, but it's essentially a dinosaur that seems to be running on one toe, and it seems as though the authors of this new paper from this past year found the dinosaur that created those footprints. Vesperosaurus seems to have ran on one toe, where the raptor dinosaurs would have lifted up the inside toe and ran with their distinctive claws. It seems as though Vesperosaurus would have lifted up the inside and the outside toes, running essentially on just the single middle toe. Now, Vesperosaurus was not closely related to the raptors, so it didn't have the large sickle claws that the raptors are famous for. Rather, it's much more closely related to things like Carnotaurus, although still slightly separate from them. The exact reasons Vesperosaurus ran on just a single toe are unknown. Potentially it may have just thought, hey, the sand that I'm running on is really hot, and ran on one toe, and over time evolved to run on just one toe. But it just shows how unique the feet of different dinosaurs can be. One of the most unique kinds of feet comes from the Tyrannosaurs, as they had what's called an arctometatarsus, meaning that the middle toe bone would have gotten pinched between the others, and this is an adaptation that's very good for long-distance running. However, some of the first and smallest tyrannosaurs in North America didn't necessarily have quite that same adaptation. Two different early tyrannosaurs coming from North America were described this year: Moros intrepidus and Suskityrannus hazellate. The first, Moros, would have come from Utah and would have been about the size of a deer, much smaller than the later tyrannosaurs that would come to dominate the same region, such as Lythronax or Teratophonius. The most interesting thing about Moros is its presence in North America 90 million years ago, slightly earlier than it was thought that tyrannosaurs were able to migrate over to North America during the Cretaceous. This was also only 20 million years after the disappearance of animals like Acrocanthosaurus, which, while they still may have been on the continent, don't show up in the fossil record. Acrocanthosaurus would have been the dominant predator of the more early Cretaceous, and its disappearance signals a pivot from the more Allosauriod-dominated environments to more Tyrannosaur-dominated environments. Suskityrannus, on the other hand, comes from New Mexico, and seemingly represents a juvenile specimen. This juvenile specimen would have been about the size of Moros. However, it potentially could have grown about 20 feet long, being much larger than Moros and more dominant in the environment, helping to show how the lifestyles of these tyrannosaurs would have shifted over time as they evolved into larger and larger forms. The find of Suskityrannus was announced at the Arizona Museum of Natural History, which has a very good model of it as well, if you want to see that, particularly in comparison to animals like Tyrannosaurus rex, which are more glorified by the media. Despite their very small starts, that's much less known. Going from the opposite direction, we're going to look at some very small animals that had some very large relatives, and that's going to be the sloths. Modern two-toed and three-toed sloths have pretty much the same niche. They're slow-moving, hang out in trees, and eat leaves. But they're not that closely related, especially when considering the various types of giant ground sloths that used to live during the Pleistocene. What's been fortunate for researchers with many of these ground sloths is that they died so recently that some of the bones still preserve parts of the sloth DNA. And this has helped to mix up a lot of the sloth family tree. Based only on the shape of bones, which is mostly what we have from these giant ground sloths, we had once thought that the family tree of the sloths was far different than what the DNA has shown it to be. One of the graphics from the paper is very good at showing this, with the new DNA analysis being shown on the left, and what was formerly thought based just on the morphology of the bones being shown on the right. As you can see, there's a lot of changes happening in this family tree, and it really helps to show that morphology isn't the only thing that we need to be able to base our different ideas of how different animals are related on, and makes it very unfortunate that we're not able to get DNA from even older sources. While getting DNA from older animals is very difficult, it isn't necessarily impossible, and we're not going wildly far back in time, only about 1.8 million years ago, in a new study that looks at a tooth coming from a rhinoceros. By doing an analysis of the different elements and protein strands that they would have made up that were inside of the tooth, scientists were able to devise what the tooth's proteome would have been. A proteome can help us understand the DNA of an animal. Each cell has an individual proteome, which is just the proteins that it produces. For example, in the pancreas, there's beta cells which produce insulin. This insulin would be a proteome and a marker of that proteome in beta cells specifically. I mean, it doesn't work for me, but for most people at least. Using this proteome, the scientists were able to essentially reverse engineer what the DNA of the animal would have looked like, as it would have still needed to be very specific to produce the exact proteins in the exact same pattern that were produced for the tooth. What this has helped to do is shed new light on the prehistoric rhinos of the Pleistocene, and shown that some species that were thought to be the same genus may actually not be. This, combined with the sloth paper, really helps to highlight just how important genetics can be to understanding the paleontological record, and how there needs to be a lot more specific research done in bringing new and novel approaches to genetics into the paleontological sphere. Having genetic material is very useful for helping to understand when different species started to diverge, but sometimes you don't need something that specific. Sometimes certain fossils can be so unique that they help us to understand when certain health problems arose. For example, cancer was found in a prehistoric turtle over 200 million years old. It was a bone cancer, so that would have definitely helped the preservation as opposed to something like a lung cancer, which would be harder to preserve in the fossil record. That said, the similarities between what is seen as a tumor in this prehistoric turtle seems very similar to what is found in modern-day bone cancers, and understanding the long history of these different kinds of diseases can help us prepare better for the future. This is the same as has been found recently in a fossil of a mosasaur coming from the Permian. The mosasaurs were aquatic reptiles, and one of these fossils shows signs of scoliosis, and it seems very similar to what is found in both humans and other animal species today. Understanding this long history can do the same as the cancer in helping us understand just how to address these issues potentially in the future. And finally, for injuries and disease, we have a mosasaur that showed signs of arthritis. It was an infectious arthritis, meaning it would have had a wound that got infected, and that infection would have moved into the joints, which would have caused great amounts of pain for the animal during movement. The fossil also shows that it likely didn't live very long after the arthritis set into effect, and so it very much could have been one of the causes of the death for the animal. These 3 papers can help to show how these medical concerns likely aren't going to go away overnight, as they've been in the fossil record at least for millions of years, or potentially hundreds of millions of years in some of these cases. The need for medical care in order to try and address these problems in the modern day is still important, as, like I said, they aren't likely to go away overnight. And so we need to make sure we are taking care of each other, as it is part of what made humanity as successful as we are. And finally, something that reflects some hope for the future. In 2018, the National Museum of Brazil burnt to the ground. And this past year, they were able to announce a new fossil coming from the ashes of the museum. The fossil has been shown to come from an Astarchid pterosaur, one of the largest animals to have ever flown, coming from the late Cretaceous period. While the species hasn't been given a name, the fact that it was found and will be eventually identifiable and used for study helps to just reinforce that there is at least some hope for the future. However, while the Brazilian museum only destroyed a man-made structure, that doesn't mean we should overlook the fires that are currently ongoing in Australia, which have killed over 500 million animals. More importantly, there are also multiple people that have gone missing or potentially have been killed by these fires, and the government seems to be taking a very lax view on it, with the Prime Minister during some parts of it having fled the country to take a vacation. In Brazil, similar fires went through parts of the Amazon rainforest, and the government took a very similar view, not being very concerned about these fires. We need to make sure that we, as a community for paleontology and for the planet, are taking direct action to try and help prevent these fires and hold the governments accountable for their lack of action in preventing climate change and global warming, and making sure that they are taking care to make sure that they are protecting the people who will be most affected by both of these. Until people like us are able to get more involved and help address these issues, disasters like Hurricane Maria or the fires that are happening currently will only continue to get worse. So please, take direct action, contact whichever representatives you can in whatever countries you're in, and try and make some change. Hi everyone, thanks for watching our year in review video, and just look at this cute little baby. He's just the best. He's just the best. He's very much the best thing to come out of 2019. He's the most wonderful thing in the world. Lots of plans going ahead for the future, including with little baby, so hopefully you will all have as good of a 2020 as ours looks like it's gonna be. Be safe, take care, don't go extinct.